Welcome back. Today we're talking metacomposites for spacecraft. And yes, fewer bad puns than chemistry class. Why did the scientists install a door knocker on their lab? To win the Nobel Prize. Let's jump in. Here's a quick summary. We'll look at a futuristic meta-composite for advanced spacecraft, what it's made of, how to build it, and why it matters. The material mixes metals like tungsten, titanium, cobalt, and aluminum, plus cerium, germanium, quartz, silicon, bismuth, and crushed diamond for top-notch heat control. Building it takes 3 steps: 3D printing for the main shape, liquid phase sintering with bismuth to fuse it, and atomic layer deposition for strong, tiny bonds. This composite could beat regular aerospace materials. It's tough, handles heat, and shrugs off thermal stress thanks to smart design. It also blocks radiation with bismuth and tungsten and uses aluminum to deflect cosmic rays. With quartz and silicon, the material can sense damage and adapt, like a smart skin for the ship. There are big challenges ahead, but this roadmap shows how we might build materials ready for the wildest missions in space. Introduction. Conceptual framework for a metacomposite. Definition and vision. Why can't you trust an atom? Because they make up everything. The design of advanced materials for aerospace applications has long been governed by the trade-offs inherent in using homogeneous substances. A material may be strong but heavy or lightweight, but unable to withstand extreme thermal loads. The query for a metacomposite for a spacecraft suggests a departure from this traditional paradigm. The term metacomposite, as envisioned, is not merely a mixture of elements, but an architected material where its extraordinary properties are not simply the sum of its parts. Instead, they arise from a meticulously controlled hierarchical structure where composition and function are graded and optimized at multiple scales. This concept aligns directly with the principles of functionally graded materials, which are defined by their spatially varying composition and microstructure, resulting in a continuous transition of material properties across a component's volume. The proposed composite, with its distinct combination of metals, ceramics, and functional elements, is a prime example of such a material, with its final performance dictated by the precision of its fabrication. The material's design, from its bulk structure to its atomic-level interfaces, necessitates a multidisciplinary approach that synthesizes metallurgy, ceramic engineering, and advanced manufacturing. The user's vision of building this material layer by layer, atom by atom, using bismuth as the glue, is a powerful conceptual synthesis of cutting-edge fabrication techniques, and this report will deconstruct this vision into a scientifically plausible roadmap, demonstrating how seemingly disparate materials and processes can be integrated to achieve a single, monolithic, and multifunctional structure. The analysis will validate the conceptual framework by linking each material's properties to a specific functional role and proposing a viable, albeit hypothetical, manufacturing pathway to realize the design's full potential. Scientific premise and scope of analysis. The primary objective of this report is to provide a detailed, expert-level technical review of the proposed metacomposite. The scope of this analysis is multifaceted, beginning with a foundational examination of each constituent material and its intrinsic properties. This is followed by a detailed description of a conceptual, multi-stage fabrication process, which addresses the challenges of integrating materials with highly divergent properties. Finally, the report synthesizes this information to describe the theoretical performance of the completed composite. focusing on its thermomechanical resilience, radiation shielding capabilities, and embedded functionalities. The report will also contextualize these properties by comparing them to established aerospace materials, thereby providing a clear, data-driven assessment of the composite's potential advantages and limitations. The analysis is presented with a formal, academic tone, grounded in the principles of material science, thermodynamics, and additive manufacturing. The constituent elements, a primer on materials and their roles. Did you hear about the chemist who was reading a book on helium? He just couldn't put it down. The proposed metacomposite is a complex amalgamation of metals and nonmetals, each selected for its specific properties and intended functional contribution. The material is not a simple alloy. Rather, it is a precisely engineered structure where each component occupies a distinct position to contribute to the material's overall performance. This section provides a primer on the properties of each constituent element and its proposed role within the composite. Refractory and high-strength metals, tungsten and titanium. Tungsten serves as a primary structural element in the high-temperature backbone of the composite. It possesses the highest melting point of all metals at 3,422 degrees Celsius and the lowest vapor pressure at temperatures above 1,650 degrees Celsius. This property makes it exceptionally resistant to the extreme thermal environments of space travel. In its pure form, tungsten is a hard, steel-gray metal that is often brittle, but it becomes malleable when purified. It exhibits a remarkably low coefficient of thermal expansion, which is critical for minimizing thermal stress when combined with other materials. Its high tensile strength at temperatures over 1,650 degrees Celsius, combined with its excellent corrosion resistance, makes it an ideal candidate for load-bearing sections exposed to high heat. For fabrication, its high melting point often necessitates formation by sintering. Titanium is selected for its high strength-to-weight ratio, which is superior to that of any other pure element, with a density of only 4 51/100 grams per cubic centimeter. It is approximately 60% denser than aluminum, but more than twice as strong as the widely used 6061 T6 aluminum alloy. Titanium is a lustrous metallic white metal known for its ductility and high tensile strength. It is a dimorphic allotrope with a hexagonal, close-packed A form transitioning to a body-centered cubic V form at 882 degrees Celsius. A key property of titanium is its ability to form a thin, non-porous passivation layer of titanium dioxide upon exposure to air, which grants it excellent corrosion resistance to oxidizing acids and chloride solutions. However, the metal loses strength when heated above 430 degrees Celsius, which dictates that its use must be restricted to specific areas of the composite where thermal loads are managed. Lightweight and conductive metals, aluminum and cobalt. Aluminum provides a low-density foundation for the composite, with a density of about 1/3 that of steel or copper. Its high strength-to-weight ratio is essential for structural applications, where minimizing mass is critical for payload and fuel efficiency. Pure aluminum is a soft, ductile, and malleable metal with high electrical and thermal conductivity. Similar to titanium, it forms a protective, natural oxide layer on its surface that provides excellent corrosion resistance. However, it is vulnerable to alkalis, acids from unseasoned wood, and certain chlorides. Its low melting point of 660.2 degrees Celsius and high coefficient of thermal expansion are significant challenges for multi-material fabrication, as they can lead to warping and fatigue. Cobalt is included for its magnetic properties and its ability to enhance the mechanical resilience of the composite. It is a hard, gray metal that is resistant to oxidation. While it can be brittle, it is also ductile and somewhat malleable, and its natural magnetic properties can be enhanced through alloying. the addition of cobalt can contribute to the overall toughness of the composite. Exotic and functional elements: cerium and germanium. Cerium is a soft, ductile, and silvery white lanthanide metal. It is highly reactive and tarnishes when exposed to air, burning readily at high temperatures. Its reactivity can be leveraged for specific applications, such as a chemical scavenger in a vacuum. Cerium also exists in two crystalline forms, with the G phase having a face-centered cubic structure. Its ductility and unique chemical properties make it a versatile, albeit reactive, component. Germanium is a grayish-white, lustrous semiconductor with chemical properties similar to silicon. It is brittle under standard conditions. As a semiconductor, germanium can serve as a functional element in embedded electronics for sensing and data processing, similar to silicon, but with a different band gap that may offer specific advantages in certain thermal or electronic conditions. The nonmetallic and ceramic components: quartz, silicon, and diamond. Why was the ceramic pot so good at keeping secrets? Because it was fired up to be non-porous. Quartz, a form of silicon dioxide, is a crucial component for embedded functionality. It is one of the hardest naturally occurring minerals, resistant to corrosion and high temperatures. A key property is its piezoelectricity, which is the ability to generate an electric potential when subjected to mechanical stress. This characteristic would enable the composite to function as a distributed sensor network, monitoring for micrometeoroid impacts, structural strain, and fatigue. A key property is its piezoelectricity, which is the ability to generate an electric potential when subjected to mechanical stress. This characteristic would enable the composite to function as a distributed sensor network, monitoring for micrometeoroid impacts, structural strain, and fatigue. Quartz is also chemically stable with a high melting point, making it suitable for refractory applications. Silicon is the quintessential semiconductor, forming the basis for integrated electronics and sensors. With an atomic number of 14, it is the second most abundant element in Earth's crust. Pure silicon is a hard, dark, gray solid with a metallic luster and a diamond cubic crystal structure. Its semiconductor properties allow for the creation of p-n junctions and transistors, which could form a continuous, integrated circuit within the composite's matrix. At red heat, silicon reacts with oxygen to form a surface layer of silicon dioxide and with carbon to form silicon carbide. Diamond is perhaps the most critical non-metallic element in the composite. As an allotrope of carbon, it is the hardest, least compressible, and stiffest known material. Its most important properties for this application are its extremely high thermal conductivity of up to 2,200 watts per meter Kelvin and very low coefficient of thermal expansion of 1/1,000,000th per Kelvin. These attributes make it an ideal reinforcement for thermal management applications, such as drawing heat away from internal systems or acting as an erosion-resistant surface. However, diamond presents a major challenge: its inherent poor wettability with a metal matrix. This poor interfacial bonding is a limiting factor for the thermal and mechanical properties of diamond metal composites. This problem must be overcome with an intermediate carbide layer to facilitate a strong metallurgical bond, which can significantly enhance the composite's properties. The low melting point matrix and shielding agent, bismuth, Bismuth, the proposed glue, has a very low melting point of 271.5 degrees Celsius. This characteristic makes it an ideal liquid phase former for sintering processes. In ceramics manufacturing, bismuth oxide is used to produce a liquid phase at temperatures as low as 738 degrees Celsius, which aids in the densification of other materials. In a similar vein, molten bismuth would infiltrate the pores of a pre-sintered compact, binding the other elements together and creating a dense monolithic structure. Beyond its role in fabrication, bismuth is a crucial component for radiation shielding. As a high atomic number element, it is highly effective at attenuating gamma and X-rays. The inclusion of bismuth alongside tungsten allows the composite to function as a dense, high-performance radiation shield, with its mass attenuation coefficient showing a strong correlation with its concentration in the material. Carbide ceramics, the interfacial and structural backbone. Silicon carbide is a carbide ceramic with exceptional properties for aerospace applications. Its high thermal conductivity, 3 to 5 times higher than silicon, wide band gap, and radiation hardness make it uniquely suited for extreme environments. SiC's crystalline structure and strong atomic bonds provide a high displacement energy threshold, allowing it to withstand high-energy particle bombardment without significant degradation, a critical feature for long-duration missions. Its low coefficient of thermal expansion minimizes mechanical stress during rapid thermal cycling, and its chemical inertness provides resistance to oxidation and atomic oxygen, a major threat in low Earth orbit. The composite will also rely on carbide layers formed at the interfaces between the metal matrix and the diamond particles. Without a suitable intermediary layer, the poor wettability between diamond and metals like aluminum results in weak interfacial bonding, which compromises the composite's mechanical and thermal performance. A thin layer of a carbide-forming metal, such as tungsten or titanium, can be applied to the diamond particles prior to fabrication. This layer reacts to form stable carbides, which form chemical bonds with the diamond and also combine with the metal matrix, thereby creating a strong metallurgical bond and significantly improving the composite's strength and thermal conductivity. The following table summarizes the key properties and proposed roles of each constituent element. As we've explored, metacomposites for spacecraft are a marvel of modern material science. Metals, ceramics, non-metallic elements, structures that are stronger, lighter, more resilient than ever before. From the sensor-rich networks enabled by quartz silicon to the unmatched hardness and thermal management of diamond and the exceptional shielding properties of bismuth, each component plays a critical role in pushing the boundaries of what's possible in space engineering. The fabrication methods such as liquid phase, sintering, advanced interfacial engineering with carbide layers ensure that these materials not only perform under the most extreme conditions, but also maintain their integrity over long-duration missions. The result? Spacecraft that are smarter, safer, better equipped to handle the challenges of deep space exploration. Metacomposites represent a leap forward in our journey beyond Earth, offering the promise of lighter launches, more durable satellites, habitats that can withstand the harshest environments in the solar system. Their unique blend of properties and innovative manufacturing techniques will undoubtedly shape the future of space missions. If you found this deep dive into the world of advanced spacecraft materials fascinating, Don't forget to like, subscribe, and share this video with fellow space enthusiasts. Your support helps us bring you more cutting-edge content every week. Until next time, keep reaching for the stars.